Welcome. This video is about incoming solar radiation and what happens to this energy from the sun as it approaches Earth's atmosphere and eventually the Earth. So, incoming solar radiation. We can shorten these three words to insolation. So when you see insolation, that is referring to incoming solar radiation, not insulation, that is like the stuff that's in between your walls and stuff to keep you hot and cold. Incoming solar radiation. And like I said in this video, we're talking about what happens to it as it approaches Earth's atmosphere and Earth. So insolation pathway. So the basic chain of events that happens, the process that this energy from the sun takes to get to us, for you to feel it, first is going to be called, or the first step is scattering. Scattering. So as energy approaches our atmosphere, we've got the Earth. Okay. We've got the atmosphere, which goes, it's about 300 miles away from Earth's surface. And then floating around in the atmosphere are gases and particulates. Later in the notes in I think chapter 5, you'll look at information about how our atmosphere is actually composed and about those particulates and about all the different gases in them. But as sun's radiation, as this incoming solar radiation approaches the Earth, it hits our atmosphere and then hits these particulates and gases and gets scattered and kind of absorbed and redirected and scattered. It's the same way as if you shine like a flashlight in a dusty room, you can see those beads of light kind of being scattered out by dust particulates. Or how light is scattered as it shines through water in a pool or in the ocean. Scattering. The more particulates and gases, the more crud that there is in the atmosphere, the more effectively those that incoming radiation is going to be scattered. So easy example of that is if you go to the beach and you go to any of our local California beaches, we have waves with a sandy bottom. So that those waves pick up particulates, sand, from the bottom, and there's turbulence in the waves, and so it picks those up and turns them around. So that when you look down in the water, you usually can't see your feet in California beaches because of all the particulates. And so those particulates are obscuring visible light, they're obscuring solar radiation as well, but they're blocking out the visible light so that you can't see your feet in the water. If you go to a different beach where there aren't waves with a sandy bottom, then the water is going to be a lot more clear because there's not as much sand picked up, that's less particulates. So visible light as well as solar energy can pass through that clear water more easily because there isn't particulates filtering and scattering it out. So scattering happens with incoming solar radiation. One of the ways that we can tell that this happens is with the visible light spectrum. So this is like a super common little kid question, as every kid says, why is the sky blue? Well, the sky is blue because of scattering, based on the thickness of our atmosphere and the amount of particulates and gases in it. Visible light from the sun approaches Earth, and by the time it gets to you, here you are, standing on Earth. By the time it gets to you, the other parts of the visible light spectrum have all been scattered out. So the shortest wavelengths, red, orange, yellow, are all the, those are the shortest wavelengths. My bad. Those are the longest wavelengths. Violet and indigo are the shortest wavelengths. Blue is the second shortest. And so based on the thickness of our atmosphere, violet and indigo light are all scattered out, and we're left with this blue visible light. So why is the sky blue? Because incoming solar radiation is filtered and scattered out by this thickness of our atmosphere. So if we had a thicker atmosphere or more particulates in our atmosphere, then more visible light would be scattered out, and our atmosphere would be a different color. If we had more or thicker atmosphere, then the light coming through it that we saw would be like a yellow, orange, or red color. You can also think of that as like during sunsets, as the sun is lower on the horizon. So if you're still this person over here, but the sun is way down on the horizon, so it's over here. And in order for you to see that visible light coming from the sun, it's got to pass through a whole bunch more atmosphere to get to you than it did when it was directly noon. So by the time this setting sun visible light radiation gets to us, it's passed through a lot more atmosphere, and the violet indigo light is scattered out, the blue light is scattered out, and you're left with the yellow, oranges, and reds that you see in a sunset. And then if you think about sunsets, if you have more atmospheric particulates, so if there's a fire or if you're in a polluted city, then the sunsets are more vibrant, more colorful, and you get more of like dark red colors that are pretty, but also an indicator that there's a whole bunch of crud in the atmosphere filtering out sunlight before it gets to you. Okay, so that's scattering. Not only is visible light being scattered out, I use that as like the focus because you can see it more approachable, but along with that visible light, a bunch of solar energy and thermal energy is being scattered as well. Next step, so a bunch of that incoming radiation is scattered out. Next thing is it hits some surface that has an amount of reflective ability, or reflection is the next step. Now when we're talking about reflection, we measure reflection as albedo. Down there in your notes it should say albedo is the reflective ability of a surface or object. So you can just think of that, reflective ability. So things that have a high albedo. This whiteboard is glossy. It has kind of a high albedo, so if you can see a glare of me coming off of it, it's because of its albedo ability. Generally, light-colored things, white things, have a high albedo rating. Things that are dark or matte, like a flat surface, have a low albedo rating. Around where you live, if there's black asphalt on the ground, like a parking lot, that has a low albedo, so it has low reflective ability. And things that are near you that might have a high albedo would be like light or white-colored concrete that reflects more energy. So natural surfaces that reflect well. Number one, the surface that's responsible for reflecting the most solar energy is clouds. So clouds are light colored, usually. They kind of vary in color to us depending on how much water they have in them. If you see dark clouds, they're just dark because they're actually blocking out incoming solar radiation and you don't see the sun, so it's kind of a shadow that you're seeing if it's dark clouds. But at any given point, clouds cover about half of Earth's surface. 50% of Earth is covered by clouds all the time. So that's 50% of Earth that's covered in a reflective surface. Now, if the clouds are thin, they probably don't reflect as well. If the clouds are thicker, they probably reflect more. But clouds, number one most reflective surface. Second most reflective natural surface is ice or snow. You can write one of those, whatever you want, doesn't matter. Ice or snow, frozen water. Now that pound for pound is more reflective than clouds, but there's much more clouds covering the Earth than there is ice and snow. So ice and snow are kind of only available seasonally. So if it's winter in a place, you might have snow, depending on what latitude it is or what altitude it is. Ice and snow are reliably going to be found in Antarctica and around the Arctic, like in Greenland, or in like northern Canada, Russia, northern Europe. So at those high latitudes, you're getting a low angle of solar energy anyway, so they have kind of a minimalized effect of reflection because it's a low angle of energy. It's just bouncing off anyway. But ice and snow are reflective. You also have ice and snow at high altitudes. If the Earth was covered in more ice and snow, then our overall temperature would be colder because those higher amounts of ice and snow actually reflect more solar energy, causing cooling to increase. And so in like a modern climate change problem, this is something that's going on right now. So we have chunks of ice that are falling off of Antarctica, and we use like US states as a unit of measurement. So like sometimes you'll hear on the news that a chunk of ice the size of Rhode Island or New Jersey or some other like small East Coast state fell off of Antarctica. So the problem there is you're losing a cooling surface. Ice and snow, glaciers end up acting like an air conditioner for Earth. They're a cooling surface because, yeah, they're cold. That's not the point, because they reflect energy back out to space. So when you have these, Earth stays colder. So these fall off of Antarctica, you lose a cooling surface, and you replace it with water. Water has a lower albedo, and it ends up absorbing more solar energy. So it acts as a heating surface. Oceans are a heating surface on Earth. So you swap out this air conditioner and turn on a heater every time a giant iceberg or a glacier melts. So these are the number one most reflective surfaces. Clouds, ice, and snow. Now, because of albedo stuff and the way that people make different things, there's this process called urban heat island. Urban heat island. This should be in your notes below. There might not be a definition with it, but urban heat island is really interesting. Kind of want to call it a phenomenon, but it's not a phenomenon. It's just a typical, very common occurrence. So that's the opposite of a phenomenon. But it's the process where human-made structures, houses, roofs, roads, parks, concrete, not parks, everything that people make, parking lots, buildings, parking structures, all absorb more energy than they reflect. And natural surfaces reflect more energy than they absorb. So that urban heat island, because of the materials that structures are made out of, urban areas are warmer than nearby not urban areas, natural surfaces. So built environments are warmer because they absorb more energy and reflect less. Urban areas, warmer than nearby open space. So nearby open spaces. Now this is something you could do as an experiment pretty much everywhere on Earth. There's a couple exceptions to this that I'll talk about at the end, but you can do this anywhere you want. And LA is actually a world leader in our urban heat island effect. So if you set up thermometers in Pasadena at PCC, let's say, we've got the San Gabriel Mountains pretty close to campus. They're a couple miles to the north from campus. You could set up thermometers all over the city of Pasadena and measure nighttime lows, daytime highs, temperature, whatever you want. And then set up a bunch of thermometers in the nearby mountains in the open space right next to us. And reliably throughout the year, you're going to find warmer temperatures in the urban developed spaces of Pasadena in any city than there are in the nearby open spaces. That's something, again, you find that in most cities all around the world. LA area, or city of LA, I think, is a world leader in that our UHI effect is up to 16 degrees Fahrenheit warmer than nearby open spaces. So if it's a 80-degree day in middle of LA, well, because of urban heat island, it's actually a 96-degree day. And if you go to nearby open spaces, then it's just a normal 80-degree day. And so it's heating caused simply because of what surfaces are made out of. So we know that's a known thing. City of LA figured out, okay, we're super warm, that's bad. So a couple of years ago, they did a pilot project where they painted a bunch of streets white and set up thermometers. And those streets that were white, the idea is since they're white, they're more reflective. They did that and it worked. Painting their streets white actually lowered the temperature of the neighborhoods that they did that project in by some amount that they decided was worth it, so that those communities during the project were actually cooler than they used to be because they had the dark streets. Now, you could do a lot of research on urban heat island. Within Southern California, it's pretty well documented. Like most geographers know this at this point, that there's a economic difference in the amount of urban heat island effect that people have, where wealthier communities usually have larger trees and more green space, so that they have a lowered effect over urban heat islands, so they're cooler. And less wealthy areas usually have less green space, more concrete, more built structures, so that they have an increased amount of or influence of urban heat island. And you can make a whole bunch of comparisons with income, race and ethnicity. In any disadvantaged community that you look at probably also has a higher UHI, just as like things are uncomfortable. Here it's a little bit worse too, because it's hotter, and now you have to pay more for air conditioning to be comfortable and not pass out and have all these other things going on. So UHI, very well documented. We know about it all over the world. City of LA, global leader in UHI, go team. But if you see the city like painting streets white or painting roofs white, those are actually steps to try to make places cooler. Because if let's say you take a building and if you paint the roof of that building white, that can lower the overall temperature in that building by about 10 degrees. So that's kind of cool. Like, do we buy an air conditioner? Do we do something else? Well, a can of paint doesn't cost very much money. You could paint a roof white. Might be against your HOA or something, but that's a good way to cool off a place. The exceptions to UHI, there's one that I know. One of my old teachers and then later on colleagues was a climatologist, and he did his dissertation on your urban heat island in city of Las Vegas. Las Vegas is unique in that it's an urban cool island, but think about the conditions of Las Vegas. It's in a desert. Deserts are already hot, okay. They have lots of kind of light colored surfaces of like sand and rock and granite rocks. And then the buildings in the city of Las Vegas are all glass, which are reflective. So like every casino is a reflective surface. And then people have built golf courses in Las Vegas, which are a vegetative surface. So then those end up reflecting more heat as well than like surrounding bare earth material. But then they water those golf courses. So that urbanization of Las Vegas has actually made the place cooler and more humid than the surrounding desert is. So like city of Las Vegas has a whole bunch of basically terraforming going on in that bubble. And so you could pick any city around the world that's similar to Las Vegas. Probably like Dubai is a good example, where it's got a lot of tall buildings made of glass that's already in a desert. So those are like, Vegas is the one exception that I know exists. Dubai is a guess. But UHI, pretty important, something that probably affects you if you live in Southern California. It's warmer where you are because of this. So like, why is it so hot? Urban heat island. And this also ends up kind of trapping more heat in the local atmosphere, so that night times are hotter because of UHI, because concrete and again human-made materials absorb that heat instead of reflect it, so that as the sun sets, they're emanating that heat, they're giving it off throughout the night. So the nights again are warmer than they should be. Like it should cool off at night. Maybe not as much with UHI. Okay. Other steps. So scattering, reflection, cool, got it. See if I can fit this in. Scattering, reflection. Number 3. Is transmission. Transmission is the ability of energy to pass through a surface. And so with transmission, we're really focused on the difference between land and water. Land, earth, dirt, rock material has low transmission rates, meaning that energy does not pass very deep into land. Low transmission. Water, so the ocean, lakes, mostly the ocean, the Earth is mostly ocean on the surface, has high transmission rates. So what that means is that when the sun shines down on the ground, energy just gets absorbed by like the first couple inches of Earth. This is an easy experiment. You can get like a turkey thermometer, one of those cooking ones that's got a metal stick and then the thermometer's on top. You can measure soil surface temperature, and it'll be one temperature. It'll be whatever it is that day. And then if you shove that thermometer into the ground 6 inches down, it'll probably be like 5 to 10 degrees colder than it was on the surface. That right there would tell you the low transmission ability of the ground, of Earth material, compared to water. Water has a high transmission ability, meaning energy passes deep into water, into the ocean. Excuse me. One way to test that, well, you could use a thermometer too. And if you get a thermometer that's waterproof, measure water surface temperature. It's going to be one thing. If you go down 6 inches, probably going to be exactly the same as what it was on the surface. If you go down a couple feet, might be a couple degrees colder. But if you go down 20 feet, once you get past like the I don't know, top couple feet, it'll probably be about the same temperature, and the ocean really doesn't drop in temperature till you get much deeper down, because sunlight can penetrate much deeper down into the ocean. One way to test that, again, visibility, is if you put on a mask and goggles and dive down underwater. Visible light is passing through the water. That's transmission rates. As far as you can see underwater, that's how far visible light is penetrating into the water, or transmitting into the water. And that visible light is from the sun. So as far as you can see down underwater, that is the distance that energy is transmitting. That's how far thermal energy is transmitting. That's how far plants can photosynthesize underwater. So you have life way deep down under the ocean because of water's high transmission rates. There's not a bunch of like subterranean plants living that photosynthesize deep within the earth, because land has low transmission rates. So if you're at the beach testing transmission ability of water, you walk across the sand and it's hot. You're barefoot. How do you get away from the hot sand? Well, you just stick your feet underneath the top layer of sand, and all of a sudden it's cold. You go from like burning hot, melting your feet off, to 2 inches down. It's like a nice, cool 60 degrees Fahrenheit. And again, that's because land has low transmission, water has high transmission. Now, what this actually does is make it so that land areas have a big difference between daytime and nighttime. They have high daily temperature variation, whereas during the day, it's going to be hot, and at nighttime, it's usually going to cool off, so you need a jacket. Water, on the other hand, doesn't really change much at all between daytime and nighttime. It's pretty much the same temperature daily, between day and night. And then most bodies of water, big ones, are pretty much the same temperature year round, except maybe if it's in a really, really cold place or in a really, really hot place. But like California's oceans only change by a few degrees annually, whereas on the land, if you go really far inland to like Death Valley, which is an extreme example, maybe that's unfair, it's 116 degrees average in the summer. That's average, not highest. And in the wintertime, it's like 65 degrees Fahrenheit. So it's a big 50 degree temperature difference. Whereas near the water, coastal places have a low daily and a low seasonal temperature range because of this high transmission ability, meaning water absorbs more energy and land doesn't absorb it and retain it very well. Last thing that happens to incoming solar radiation, number 4, is conduction. Conduction is the molecule to molecule transfer of energy. Molecule to molecule transfer of energy. So when one molecule is warmer than another, energy is going to pass from between those two molecules until they're the same temperature. So if sun is hitting these molecules, the sun's shining down, it's hitting these ones. Energy is going to transfer to the ones that are touching it until you run out of energy, until they're the same temperature. So that's conduction. So conduction is the last step. Whatever sunlight hits, incoming solar radiation, whatever it hits, metal, plastic, plants, dirt, water, people, fur, cars, whatever you want, energy is going to pass from molecule to molecule through conduction. That's all. Hope you didn't have any questions, or hope I answered your questions already. There you go. Insolation pathways.